manifold groups. This is all joint work with Daniel Groves at UIC and Henry Walton, who's at University College London. First lecture, I'm mostly going to provide some overview and state the problems I'm going to try and solve for you. I might outline the solution as one of the simpler ones, or a couple of the simpler ones. And then the next two lectures, I'll tell you what we did. So because this is, I know there are a lot of graduate students here. Let me just remind you sort of the basic how this starts. Sort of basic decision problems in group theory. So these are especially because these are going to be very relevant to what I'm talking about. At least two of them are. So these are the sort of Dave's fundamental sort of group theory problems. So I'll just list them and then say a little bit about them. So there's something called the word problem. The conjugacy problem. And the isomorphism problem. So these came up in Dane's work because he was trying to use the fundamental group to understand low-dimensional manifolds. So specifically, he was trying to use the fundamental group to understand three manifold groups. Try and distinguish three manifolds from one another. And if you have a loop in a three manifold, try and understand, is that an essential loop? Is that something non-trivial in the fundamental group? So that's where the word problem comes up. So given a triangulated three manifold, this is going to give you a finite presentation of the fundamental group. So we're always going to be working with finitely presented groups. So we're going to have, in these problems, the groups are always given by finite presentations. And the idea here is that these are written this way. We've got X and we've got R, and we have where X is just some set, and we're going to write G equals. So this is an abuse of notation. This is a presentation of some finite amount of data. This is an algebraic object of group. But what we mean by this is always just that the free group on the set X maps onto this group G. So every group is the image of a free group, and so that the kernel is normally generated by this set R. Right. So for example, we can write V plus V as so usually we leave out the set brackets and just write AB and then subject to this condition. So this is an element of the free group on A and B, AB, A inverse, B inverse, just saying that the commutator normally generates the kernel from the free group we're going to Z plus Z, and using the standard map, and that's called the standard presentation. And so the deal is we have this finite system of data, and we want the word problem is just to be able to take an element of this free group and determine algorithmically, and I'm not going to go into detail about what that means, but determine algorithmically whether or not that word represents the trivial element of the group, whether it gets mapped to this trivial element. So given W in f of X, so determine whether or not W is equal in this presentation. So we're going to call this data well, let me just write equals sub G, meaning equals in G, the trivial element. So, okay, and then the conjugacy problem. So given two words, W, so determine whether or not, I'll just write if, there exists some sort of G also in this free group on the set X, so that W is a conjugate in G of V. So this is a topological, these are all topological problems. So this is asking for a loop in a manifold, whether it bounds a disk. Here this is asking whether parent loops co-bound in annulus, right? So this is closely connected to the stuff that Danny was just talking about. And of course the isomorphism problem, you can guess what that is. So given two presentations, is there an isomorphism? What seems right? Is there some sort of isomorphism between them? Now, as you know, as most of you probably know, in general, these problems are totally insoluble. So this follows from classical work of Turing and others on sort of the existence of recursively enumerable but not recursive sets. So in general, these problems are impossible, provably impossible. But in many particular cases, many natural classes of groups, we can solve problems like this. So solvable in many natural classes. So examples that would be relevant to us, so the word problem is solvable in so-called hyperbolic groups, which were mentioned also in Dan's talk, automatic groups, polycyclic groups. Many sort of natural situations. More generally, you can encode the difficulty of solving the word problem in something called a Dane function, which is sort of measuring how difficult it is to fill disks in a space, or in this case in a sort of Taylor graph for a group, how difficult it is to fill disks. If you can measure that difficulty by some kind of computable function, then the word problem is solvable. So it's actually equivalent, that function being computable and the word problem being solvable.
Yeah. Solvable means there is an algorithm, not we can find the algorithm.
That's correct, yeah, and that's a subtle point that I'm going to completely gloss over. But yeah. So for hyperbolic groups and automatic groups, we can actually find the algorithm, and for polycyclic groups. I think that's also true. But yeah, given a presentation, you might know abstractly that there might be a solution to the word problem, but there's no algorithm to find the algorithm. That could happen. So that's the issue that Danny's bringing up, and we're going to quietly sweep under the rug, I think, from here. I may mention it once more, actually, later when I talk about how to interpret our main theorem. Okay, and so also, what else do I want to say about this? So the isomorphism problem, you can show that, so the isomorphism problem is also solvable
at least in hyperbolic groups and polycyclic groups. I don't know about automatic groups, actually. Conjugacy problem, we're not going to talk about, but let me just mention out loud that there are groups in which the word problem is solvable, but the conjugacy problem insoluble. So the other direction can't happen, right? Because the word problem is a special case of the conjugacy problem, where one of these words is the identity. Okay. Let's say too much more about that. I could talk for, well, I could talk for hours, but I'm the wrong one to listen to because I'm not the expert on this. So we'll use bits of this when we need it. And I'm also not going to say exactly what it means to solve this problem, except I'll say in words right now. So if you're talking about, at least in the word problem situation, you have, say, this is going to be some finite set, and this is going to be probably some finite set here, though not necessarily in that case. And so you can represent elements of this free group as words, just finite strings of characters. And so to solve the word problem means you build an actual, you build a machine, a computer that takes as input those strings of letters and outputs a yes or a no, depending on is it trivial, is it non-trivial. But maybe just to make it less ambiguous, outputs trivial or non-trivial rather than yes or no. It's not clear which question you're asking. So we're going to want to ask it in many different ways. All right, and so, there's an old classical theory that you know all about Turing machines, which says exactly what that means. And sort of the punchline of that is like sort of any way you try and formalize it, you end up getting the same answer, basically. What it means for something to be computable or decidable. Okay, so the problems I want to consider and this is going to be version 1, because we're going to see that this is not a very good way to pose things. So the first, let's fix some n, an integer beginning from 0, and I can ask two questions. So your favorite groups, I don't know, groups are always fundamental groups of spaces, and your favorite spaces are manifolds, right? So it's natural to try and understand which finitely presented groups are fundamental groups of manifolds. So the question I want to ask is whether you can algorithmically distinguish such things. So that's the first question. So we want to algorithmically determine which finitely presented groups are pi1 of a, say, closed, orientable n manifold. Okay. So again? For a given n. For a given n, yeah. So we're fixing n. And then, so the first problem is this. So, and we'll just call this property, property, this is how I meant to write it, sorry, m sub n. So G has this property m sub n if G is equal to one of these things, okay? And then second, so is this a decidable property of finitely presented groups? We'll see it's not, but anyway. So the second problem, we want to decide the property, a second property, maybe, A sub n, which is that G is isomorphic to pi1 of some closed, orientable, aspherical just to remind you, all I mean by spherical is the universal cover is contractible. So somehow, well, for reasons that I'll tell you in just a second, this is, at least for large n, this is a more natural property to look at. So the question, so first question, are these properties decidable in kind of this most general class of finitely presented groups? And you might guess from the fact that these sort of simpler looking problems are unsolvable that none of these problems are solvable, and you'd be right, except for when they're trivial. So they're all either trivial or unsolvable. So let me explain that now. And then I'll explain how we can rephrase them as more interesting problems. So as stated, these, so AN and MN are either undecidable or trivially decidable. Okay, so let me start with the trivially decidable ones. So if I look at, so M sub n for n bigger than or equal to 4 holds for all groups G. You may have seen this before, but let me kind of remind you of the construction. So what you can do, if you're given, so we're given some presentation. We're given G by a finite set of generators and a finite set of relations. So we're always assuming X and R sitting inside f of X are finite. So if I want to make an n manifold with free fundamental group, so what can I do? So I can take, if n is at least 3, this part works. So I can take Sn minus 1 times S1. So that gives me something with Z fundamental group. And now I can take a connect sum of a bunch of those, right? So, so we're going to start with sort of M, let's call it N. Which is going to be just take a connect sum over the generators of copies of Sn minus 1 times S1. So the fundamental group of N is isomorphic to the free group on X. Get rid of no connect sum. If I have 2 manifolds with the same dimension, I can scoop out little balls in each of them and glue them together along the resulting boundary. So on the level of fundamental group, I've just taken the free product. So so now realize R as an embedded 1 submanifold in N. So sort of the picture here, like I've got, I can think of taking, S3 and I've sort of connected a whole bunch of these S1 cross I's to pairs of spheres here, if you like. That's one way to think about it. This gives you the same thing. And now I'm going to take these. So these words only matter up to conjugacy, right? So I can think about them as just free homotopy classes of loops, exactly like what Dan was talking about earlier. And say I've got, something like this. And, I can suppose it's embedded. So maybe I've got another one here. Okay. And now, let's give that a name, C. And now I can remove, kind of open a regular open neighborhood of C, and now I'm going to get some manifold with boundary, right? So the boundary, so this gives me, call this n, I don't know, n hat. So the boundary of n hat is a disjoint union over R in R of, well, what do we got here? We've got S1 times Sn minus 2. So we've got S1 times Sn minus 2. And now what I want to do, I just want to glue in some kind of 2 handle to kill that element of the fundamental group. So by the way, n hat, yeah, this is the point. If the dimension is big enough, n hat's got the same fundamental group as n hat. So that's what doesn't work in dimension 3. Dimension 3, you have a different fundamental group. So now we want to glue a copy of d2 times s to the n minus 2 to each boundary component of n hat. So this gives me some sort of, we'll call it n sub g. So and we can check that the fundamental group of this n sub g is isomorphic to g. So as long as n is at least 4. Okay, so if I want to decide, so the point is M4, this problem M4, for example, is trivially decidable. You just have a machine that says, that ignores what you give it and just says yes. It's the fundamental group of an n manifold. Yes. 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 Okay. So n for n bigger than or equal to 4, all these ones. Okay. Now to say why the others don't hold, I need to tell you first what a Markov property is. So, there's a definition. So basically, yeah, so those are the only ones, those are trivially decidable. All the others are undecidable. So a property of groups is Markov. By the way, nothing I've told you yet is new. I'll tell you when I tell you anything new. This is all classical stuff. Is Markov if 2 things hold. So let's call the property P. So one, there exists some finally presented, and I'll just write FP most of the time, group H plus with the property. And then 2, there exists another finally presented group, H minus, so that, so H embedding in G implies that G does not have P. Okay? So the property M4 is not Markov, right? So there certainly exist finally presented groups, which are fundamental groups of 4 manifolds, but there's no poison subgroup. There's no way you can destroy the property of a finally presented group being fundamental group of 4 manifolds. What's that?
H minus n?
No, this is supposed to be the, there should be, I guess, a philology H minus embedding in G implies that G doesn't have the property. Is that? Yeah. Maybe I should write that. Maybe I should just give an example to make this clear. So an example 0 is the property of being trivial is a Markov property. I'll just say triviality. So you can take H plus to be 1, you can give that a finite presentation. If you like with a single generator and a single relator. H minus, you can take any non-trivial finitely presented group. So for instance, Z mod 2, which you can write as X, subject to the relation X squared. Right? So this is a trivial group. If a group contains Z mod 2, it's non-trivial, right? So, okay. So the theorem, let me just give you condition n, because this is what we're going to use. The property A sub n is Markov, right? So this, by the way, this is the same as A sub 0, right? There's exactly one closed zero manifold, it's a point. So the property of being isomorphic to the fundamental group of a closed zero manifold is the same as being trivial group. Yeah, so that's A0. So A sub n is Markov. So if I take an n torus, right? So I can take Z to the n for my H plus, and I can take Z to the n plus 1 for my H minus, right? If I have a subgroup, if it's an aspherical n-manifold group, it's, for instance, its cohomological dimension is n, and that gives you an upper bound for the cohomological dimension of any subgroup. So you can't have a subgroup that looks like nu plus 1. Okay, so the point of this is that there's a beautiful theorem of Avion and Rabin, classical theorem in this subject that says that Markov properties are undecidable. So I haven't talked about M1, M2, and M3, but you can do those. These are Markov. You might need to know some three-manifold topology to do M3. Just write exercise. Okay. So that's meant to justify the statement that I made before, which is that all these properties of Mn and An are, if I don't add some extra hypotheses on my group presentation, they're either trivially decidable or they're completely undecidable. So let's rephrase things. So what was the first undecidable problem in group theory is the word problem, right? So on the other hand, lots of groups that we like and care about, we can solve the word problem for. So that seems like maybe a natural class of groups to look at, groups in which you can solve the word problem. Okay, so let's do that. So let's restrict attention to groups with a solvable word problem. Okay, and now in anticipation of Danny's question, we'll say with a solution to the word problem. Okay, it shouldn't just be solvable, we should actually have a solution in hand.
Or anticipation.
What's that?
Or anticipation, to ask the person to answer.
Well, you could have hounded that guy.
See, in general, the 3D problems are depending on the presentations rather than group isomorphism classics approach.
Well, yeah, there are questions about presentations, but if you have two different presentations of a group, and you know that, and you know how to get from one to the other. So if you have a sequence of Tizzi transformations taking you from one to the other, then you can transfer a solution of the problems in one presentation to a solution in the other presentation. Right. So, and if they are presentations of the same group, it's this old theorem of Tizzi that says that there is a sequence. So, in fact, although, in practice you're always going to be working with a particular presentation, everything I'm talking about is somehow about the finitely presented group.
Okay, so let me just say a little bit more about what we're going to supposedly have. So we suppose, so our typical sort of input data for the algorithms that I'm going to talk about in a little bit is going to be, so it's going to be a finite presentation together with a Turing machine, or if you like, I mean, we're never going to look inside the Turing machine, so we could just have an oracle. Which solves the word problem. In that presentation. People familiar with this idea of an oracle. So I'm trying to describe an algorithmic procedure, and there's this black box that I'm allowed to ask questions of. And this black box will answer a particular question. Is this word trivial or not? Right? Now, in many situations, as I said before, hyperbolic groups, automatic groups, it doesn't need to be an oracle, it can be an actual machine. But we don't care what the machine does on the inside is the point. So. Okay, and then I think it's time to state the theorem. Oh right, well, let me just say how I'm going to refer to this. So I'm going to refer to this as a group with we'll solve a word problem. So and there's something, there's a little bit, something wrong about saying it that way because really it's a presentation. But as I just sort of waved my hands about a few moments ago, I have any two presentations of if I have a solution to the word problem in one presentation, I can find a sequence of Tizzi transformations that take me to this other presentation, and that's going to give me an explicit isomorphism between the groups presented by those two presentations. And so if I want to solve the word problem over here, I just map the word back to my original presentation, use the computer, and then use the answer. So here's a theorem, kind of, say it in the sort of most grandiose manner possible. So, so for each n greater than or equal to 0, m sub n is decidable for these groups with solvable word problems. And then and of course, when n is at least 4, I'm saying something completely trivial, as I pointed out before, right? And now for n between 0 and 3, a sub n is decidable for these groups of solvable word problems. And then, so that's the theorem, and I'll kind of draw a little a table over here to show you which of these are interesting and which of them are not. So this raises an obvious question, which is, what about a sub n for large n? So the lectures that Mark is going to give are going to tell us that high-dimensional aspherical manifolds can be really bizarre, which makes me think maybe no, but I really have no idea. So just again, I erased the original definition. This statement m sub n is that the group is a fundamental group of some closed orientable n manifold. And a sub n is that it's the fundamental group of a closed orientable aspherical n manifold. So they're slightly different questions.
Professor Knox, will lectures make it more likely the answer is yes, as it produces more examples?
Maybe. Yeah, maybe.
Yes, Jay.
No. It doesn't give, which way, does it give evidence that it's harder or easier?
I think there are examples of meter check.
Oh, okay. Oh, so maybe the answer is no to be known. Okay. Oh, okay, good. Awesome. Okay, maybe no. Okay, yeah. So maybe something by Noah? Okay. Yeah, maybe I'll follow up with you on that, because I would like to know. Well, that would be great, because that would make this the best possible theorem. So it'd be great for me, but not so great if you're trying to recognize aspherical formula groups. Okay, so let me just make a sort of table and wave my hands at it. I want to draw vertical bars, sorry, horizontal bars everywhere. Not horizontal bars everywhere. The point is that these only start to be different. Oh, I guess they're different in dimensional one, aren't they? Okay. No, for closed one manifolds. There's only one closed one manifold. And it's aspherical. Okay, so the point, the reason there's no vertical bar here, of course, is that A0 and M0 are the same, and M0 and, A1 and M1 are the same, right? So this is the question, is it trivial, right? So this is the question, are you isomorphic to Z? All right, so let me just talk briefly about those and why the word problem solves these problems for you. If you can solve the word problem, you can solve these problems.
So n equals 0. So we've got, so given group of solvable word problem, so without the word problem we can't do this, but with the word problem it's easy, right? So x is equal to some finite collection of words in the free group on x, they're just generators, but I have a procedure to tell whether or not each of these is trivial, right? So we can use the word problem to determine the truth or falsity of the statement, there exists an x I in this set so that xi is not equal to 1. And then if it's true, then G is not equal to the trivial group. And if it's false, then G is trivial group. Wow. We can write it in a number of different ways. The point is I only need to check the generators, and that's some finite process, right? So for n equals 1, so we've got this group of solvable word problem. With presentation x with relators r, and the point is that, so first of all, we can check whether G is abelian. So G is abelian if and only if all the generators commute. So commutator of x and y is equal to 1 for all x and y in the generating set. Right. And now exercise can decide if a finitely presented abelian group is isomorphic to, well, your favorite finitely generated abelian group, right? I guess we only have to say finitely presented, but finitely generated, but to decide whether you're finitely, except you need to have a presentation, so we should say finitely presented. So you can decide which finitely generated abelian group you're looking at just based on the presentation, right? And this is some linear algebra or something, right? Okay, so that tells you these guys. We already know that this one's impossible. So let's just say for a second, what is property M2? Well, either it's an aspherical surface, or it's the sphere. Yeah?
Oh, no, that was true.
Oh, sorry. Trivial. That one's trivial. Trivial. Just say yes. Sorry. This, we don't know. I'm not going to say anything about this. Unless I find out this reference from Miller, and even then I probably won't say anything in here. But okay, so M2 is really just it's A2 or A0, right? It's either. Right? So being fundamental group of a two-manifold, of an orientable closed orientable two-manifold, means either you're a fundamental group of a sphere, or a torus, or a hyperbolic surface. All of those are aspherical except for the sphere, which has trivial fundamental group. So if I can solve this, and I can solve this, then I can solve this. Okay. Right. So, do I want to, okay, so, I don't really want to talk about M3, because it involves talking about some three-manifold theory that I cleverly figured out how to skip. But basically, if you know the three-manifold theory, the point is that if you want to show you're not a three-manifold, first you want to look at the three factors, right? And you want to show that each of them is not an irreducible three-manifold group, okay? An irreducible three-manifold group, so you want to show it's not one of a finite list of finite groups, and it's not one of these guys, it's not aspherical. So you can reduce it with a little bit of work to A3. So it takes some work. But it's work that I'm not going to talk about. So, what's that? Oh, it's all good, yeah, I'm definitely using geometrization, yeah.
Some work.
I don't know how to do this without geometrization. That would be very interesting. Yeah.
I mean, to reduce it, you need to worry about the finite.
Yeah, to reduce it, I need to worry about the finite groups, yeah, and I need to worry about free product, and that's it. So I need to be able to decompose my given Wissler into free factors, which are Wisslers.
And like, no one gives you some constraints, but that's not enough to do it. I guess if you happen to be one on the list but not leading it.
Oh, you mean the constraints on the finite groups?
Yeah.
Yeah, the constraints on the finite groups are, yeah, that's not too hard to deal with. I mean, basically, there's going to be a bounded index subgroup which is cyclic if it's finite, and the bound is explicit. So it's
The problem is you could be one of those groups and without geometrization, you wouldn't know you weren't.
Yes, that's correct. Yes. So you have to use the positive curvature part of geometrization for that. Right. So really what I'm doing when I do this box right here is I'm showing that I can decide whether or not it's the fundamental group of a three-manifold which satisfies the geometrization conjecture. Yeah. And part of that is I know what finite groups can appear, and I know what infinite groups can appear. I can distinguish them from other Wisslers. Okay. So this is where this will be the second and third lectures. And this box right here, the point is that this actually follows fairly easily from some work of Groves and Wilton on limit groups. And I'm going to turn around and see if I have enough time to tell you about that. I have 10 minutes. So I'll tell you a little bit. Okay. So how to decide if you're looking at a surface group. Okay. So what did Daniel Groves and Henry Wilton do on limit groups? So one of the things they did was they showed that there's a way to enumerate limit groups. So let me tell you what is a limit group. So a finitely generated group L is it's called a limit group if it, well, I'm going to define it in terms of something else I haven't defined. So fully residually free. But there are several definitions of limit groups. All of them equivalent, but fully residually free is maybe a little bit more evocative. So we say a group is residually finite if for any non-trivial element of the group, there's a map to a finite group that distinguishes that element from the trivial element, right? So that implies immediately something which you could call fully residual finiteness, which is that if I take any finite set in the group, I can map it injectively to some finite group using a homomorphism. So that's the thing. So they're not equivalent for if the quotients are going to be free groups, but we want the stronger one. Fully residually free, and what does that mean? It means for all finite sets A sitting inside L, there is for each finite, it's a different map for each one. So for each finite subset of the group, there is a homomorphism call it p sub A from L to some free group. Which is, I can always take the be free rank 2 because I'm looking at a finally generated group. So we'll just write F2, so it's free. So that if I take p sub A and I restrict it to A, this is injected. Okay. So these are becoming increasingly, well, anyway, it's become increasingly apparent since I started doing that these are really kind of an important next class of groups to look at sort of after free groups. They're groups that are, in some sense, nearly free, but not necessarily free. So examples, well, free groups. Finitely generated. Free groups. Free abelian groups. Again, finitely generated. Free abelian groups. So that takes a little bit more thought to the first one. So the idea is that I can take, if I have my finite set in a free abelian group, I can find a map to the integers, which is injective on that finite set. And now I can send the integers into a free group, however I like. So, and surface groups are important. So fundamental groups of closed orientable surfaces. So those are key examples. There are other examples as well, but we don't care about them right now. They're all finitely presented. They're all what's called cat-0 groups. They're relatively hyperbolic. They have a lot of nice properties. In particular, all those fundamental problems that I wrote up on the board before are solvable in these groups. So they have solvable word problem. It is possible using some work I'll mention in a second to solve the isomorphism problem for these groups. Actually, maybe I won't, because I have only 5 minutes. But anyway, these are nice groups. Now, another definition. So one of the things you use these groups for is to study equations in free groups. And so a set of equations in a free group, you can really just think of as a map from a finitely presented, well, a solution to that set of equations, you can think of as a map from a finitely presented group to a free group. Well, that needs some explanation, but I'm going to skip it. So what you want to study is the set of homomorphisms from a given group to a free group. And so if G is finitely presented, then there's something called a factor set for G is a finite collection of, well, I have some homomorphisms from G to some limit groups. So these are limit groups And these are going to be surjections. So these are limit groups. So surjections on the limit groups, so that every homomorphism from G to a free group factors through one of the eta i's. Okay, so point is that the factor set is, one way you can think of this factor set is, if you think about this in terms of kind of thinking about algebraic geometry over groups. So you can think of a variety of homomorphisms from this fixed group G to a free group. And what the elements of the factor set are, they correspond kind of to the irreducible components of that, if you think of it as an algebraic set. Anyway, there's an analogy there that's not perfect, but it's pretty good. So, okay, so there's a theorem of Baumschlag, Myasnikov, and I'm going to get this wrong, Remeslenikov. And they say that so for each G finitely presented, there's a unique minimal factor set. So, for example, for G equal to the fundamental group of a surface of genus G, closed orientable surface of genus G, the factor set is just got one thing in it. So we've got eta 1 from G to any map, which is an isomorphism to the fundamental group of the surface of genus G. Now, what follows from the work of Groves and Walton is that these factor sets are actually constructible. And that basically, that more or less does it for you. So let me just, it's not exactly in their paper, but it's a not too hard consequence of the work of Groves and Walton together with some work of on the solving the isomorphism problem for limit groups, which, let me get the right. Let me get Topology and Myasnikov. What I was doing before. Or alternatively, you can use this work of Damani and Groves. So what's being used here is the isomorphism problem for these limit groups. Is that so the factor set? So given G, a group with solvable word problem, the minimal factor set can be constructed. And I'm out of time now, so what I'm going to do is I'm just going to say in words very quickly what you do from here. So you construct this minimal factor set. If it's got more than one element in it, you're not a surface group. You can conclude that you're not a surface group. If it's got exactly one element in it, either you are a surface group, and you can actually you'll eventually discover that by just rewriting the presentation. So you want something that just sits there and rewrites the presentation. This is a point which I'll get to in the very beginning of the next lecture as well. How you determine that you are a certain type of group is often, you can do this just by brute force. So the key thing you want to be able to do is decide that your group is not a surface group. And you can do that by, when you're given a factor set, that means you're actually given this map eta completely explicitly. So you can look for elements of the kernel, right? And because you can solve the word problem in G, you can recognize that you found a non-trivial element of the kernel.
So you're given the vector set in such a way that you can see that it's a surface group.
Yes, well, yeah, so you can, that's what uses, so you need to use this again here, so once you, yeah.
You know that's a limit group, so you can tell that that's a surface, you verify that that's a surface.
Right, you verify exactly, sorry, I skipped a step. Yeah, there's a middle step, which is you look at the image of that single factor map, and you check that it's isomorphic to a surface group. And you know which one it should be isomorphic to just by computing homology. So now you use the solution to the isomorphism problem for limit groups to see, is it a surface group? Yeah. And then you look for kernel. Okay. I should stop.